Good morning, good afternoon, evening to everyone. As she mentioned, my name is Jeff Robertson, and I am business development team with Simufact Engineering. And so thank you again for joining us. We're going to walk through this presentation. This was originally delivered at the AWS presiding with the FabTech event earlier this year. So the primary challenges with many weld distortion and residual stress has traditionally been mitigated or managed by two primary ways. One would be the experience of the welding engineer and good old-fashioned trial and error. Unfortunately, the experience and intuition of the welding engineers is not perfect and not perfectly predictive. And with today's aging workforce, a lot of this tribal knowledge is going to go away when those individuals retire. Additionally, traditional trial and error is generally expensive and time-consuming. There are modeling tools that can predict weld-induced distortion and stress. However, these tools need to be more accessible. They're typically difficult to utilize and generally not available to those people who do not have extensive FEA or finite element analysis experience. As I mentioned, what we would call legacy simulation tools are difficult to employ. There's a huge number of settings, difficult to create things like weld beads or boundary conditions, clamps, fixtures. One has to often prescribe contact, tell the software when bodies are in contact, and to even get into the point where you have to edit the text file that drives the simulation. All of this makes it not practical for people who are not very well versed in CAE. So I asked the question, well, if it wasn't limited by the complexity of the software, who would be the right group of people to utilize the simulation? And my opinion, it's the welding engineers, or at least people a little closer to the shop floor. Looking at the difference between the two groups, there's a significant gap between the environment of the CAE analysts, as I described, and the welding engineers. So they're separated by a number of things that we'll look at: experience, work environment, organization, time zone. So on the left-hand side, typically this CAE analysts and designers have an education or experience, master's, PhD in some computational methods or some other high-level work. They work in a computer lab or design studio. A lot of times it's within the design group, and oftentimes it's far away from the manufacturing or even overseas. By contrast, the welding engineers are welding engineers, or in many cases, welding engineering technicians or technologists. They work on the shop floor, close to the fabrication and manufacturing, and are in the US or very close to where the parts are actually being manufactured. So what if we enabled the welding engineers to run their own simulations? So this is where the concept of democratization of welding CAE or welding simulation comes in. There's several advantages to this. First would be the opportunity to have greater amounts of analysis being done, because you have a greater number of people that have access to it and can make it work. Also, these welding engineers have the insight to realistically model the process. They get welding and they understand how to realistically model it and what sort of steps to take to mitigate weld-induced distortion and stress in the real world that can be applied to the finite element analysis models. This also reduces the time and communication loop necessary or required to build and iterate on models. If every time they created a model, you had to go back through and communicate between the welding engineer and the designer, and then the designer then has to go and create the model and then solve it, send the results back, and then another meeting, and another meeting. And each of these times, each of these iterations or communication loops is time and the opportunity for error within the communication. Generally, it also increases the base of knowledge for the organization. So the question is, how do we do this? How do we democratize welding process simulation? So the first part is simplify or a simple FE, or finite element meshing process. And the second is a process-oriented user interface. So something that mirrors the shop floor, mirrors the process on the shop floor, minimizes the requirement for FEA, so you don't have to be an FEA expert. Something that's capable of modeling all the different welding processes, and also simplifies a lot of the process modeling. The benchmark that we always use is time from CAD to results. So the first step would be meshing. For any of you out there that are familiar with finite element analysis, you know that this can be very painful and take a long time in many cases. So with the MSC Apex tool that we utilize within our welding workflow, this time is reduced dramatically. So we utilize, for flat surfaces, as you can see here, a mid-surface where we create a 2D mesh. And then also for bulkier parts like these rings, you'll see we can create a volume mesh. So in this case, we're going to create a mesh in about 30 seconds. So here we're going to go say what part they want to mesh, and then to be able to seed that part and actually create multiple elements through that thickness, say 3. Then we're going to create the surface mesh for this other part, the side. And perhaps we want to seed that mesh to give it a little bit of refinement closer to the welded area. And you can see that the mesh was created. So from this 2D mesh, we would then export from MSC Apex, and then upon importing into Simufact Welding, that mesh would automatically be expanded to a solid volume, utilizing either a solid mesh or a solid shell. As I mentioned, this is becoming a semi-automated process. We do actually have subroutines that can do this, or much of this work, in an automated fashion, taking something that would have typically taken many, many hours or days down to, say, less than 10 or 15 minutes. So the next aspect of it that we discussed was the process-oriented model setup. And I'm going to go ahead and click this animation, let it play, but basically we're going to go through, and this same model that we're utilizing as this outrigger, something you would see on, let's say, a bucket truck. I'm going to go ahead and let it play, but you're going to see essentially the entire process modeling step be completed in about 3 minutes. So within this workflow, you can see that, again, we're going to go ahead and basically import the geometries. And you have an object catalog on the right-hand side, which is where all the parts where all the different components are imported. You can select a variety of processes and basically utilizing a automated approach or semi-automated to utilize wizards, and that sort of thing can accelerate the import and creation of the model. So this is the mesh that we just created. We'll go ahead and create a weld line. And we're going to go back through some of this stuff in a little bit more detail in later slides. But as I mentioned, being able to go and have a workflow that mimics what's happening on the shop floor is very similar to what you would actually create. I mean, what do you need when you're building a welding, a part for welding or setting up a process? You need parts, It has fixtures. The parts are made of a material. You have weld lines. Those welds have a filler oftentimes associated with it. Also the weld settings, voltage, amperage, travel speed, and a heat source. And so being able to essentially set up the welding simulation to mirror what you're doing on the shop floor without having the extra complexities associated with traditional finite element analysis makes it much easier and quicker to set up. Again, being able to have simple drop-down menus and dialog boxes that control these things. We're looking at a very simple part here, but you can do this with hundreds of welds and varying weld geometries, and still be able to very effectively, quickly, and simply do things like creating weld beads, creating clamps and fixtures, things that often would have taken a great deal of time. And this is actually one aspect of it, the fillet generation, that saves a tremendous amount of time. You can see that we're actually creating the weld bead right there, and if you want to, you can vary it, and it's automatically updating the weld bead geometry. So a lot of these things we've simplified, as I mentioned, modeling weld beads, paths, fixtures, clamps, tools, tack welds, etc., and then no need for text file editing required. So that was basically the entire modeling process, give or take, in about 3 minutes. So as we mentioned, going through in a little bit more detail, now you can see the remainder of this model being set up, being able to quickly define weld paths and having the ability to organically create weld geometry. Basically going to go through the same thing that we saw a second ago in a little bit more detail. So you're basically picking the nodes along this intersection, and it's automatically selecting the points along that line. And then that becomes a weld line. And you could easily change the orientation or start from one end to the other. And then we just drag that weld line onto our, what we call robot or welder. It should be, in my opinion, a welder, not a robot, but and then you can vary the orientation of the part. So if you wanted to have the torch have an inclination angle, again, this is going to affect where the heat source is going to impact or intersect your geometry, as we'll see in a second. And then we're going to go ahead and generate that weld fillet. And you can see also that little red down below, the little red heat source. This is actually your heat source that can be adjusted, and that's the volume that the heat is, the energy is imparted to the part. So there's a good amount of control, and this is something that we're continuing to improve to make much more flexible in being able to vary these weld beads. And you can kind of play the animation, slide it back and forth to see, to follow your heat source around before you actually commit to initiating simulation. Similarly, applying clamps and fixtures is something you very often do within a welding simulation. You can see here that we're utilizing the entire fixture. Something that may or may not be relevant. So being able to have realistic clamping conditions and then flexibility to either build it in from your CAD or create it within the user interface. So within a clamp, we could utilize stiffness and force, or what we call a moving clamp. Stiffness has just stiffness, or you could apply a force as well. In this case, we'll have a stiffness, which could be translational as well as rotational stiffness. And then a moving clamp, essentially it says push in a direction, displace the clamp a certain displacement over a period of time. So in this case, it would take 1 second to move it 3 millimeters. And whatever force would be required to push that in the specified direction would be applied and that would impart a residual stress and potentially plastification of the part. Also being able to have multi-station assembly process. This is something that came out of the auto industry and tier 1s and OEMs wanting to be able to go through the assembly process and essentially go station by station through the welding process. And as you get these distorted parts, oftentimes they don't fit very well. And so being able to actually assemble them through what we call a cooling and clamping step, you can push parts together. You can, let's say, force them to over top of each other, and if there's some sort of intersection, the software would actually resolve that intersection and allow it to slide around each other, and so to be able to achieve the type of fit that's very realistic. This could also be used to take a number of pre-distorted sub-assemblies and clamp them into contact, clamp into place. Something that would have been very, very difficult to do in legacy welding simulation environments. And of course, it captures the cumulative effect of the distortion and stress. So there's, by comparison, a legacy simulation software requires significantly more amount of time and experience to employ effectively. So you would expect for a legacy simulation software, which would be a software that's dedicated for welding, however, it would be 2 or 3 times the time required to model. Whereas, let's say, a general purpose solver, so something where you're in the, something like a mark solver, where you're very much in the weeds to set these up, 4 to 8, or I've even heard 10 times the time required to model. So I jokingly sometimes say, if you do this, what would have taken you a week, it could be done in a day. What do you want to do with the rest of your week? So here's a little comparison. This is just a benchmark that we conducted. And so if you see from some of the standard steps that you would go through, CAD import, meshing, thermal boundary conditions, weld lines, heat sources, billet geometry, generation, clamps, fixtures, total modeling time, solve time, and post-processing. So with this benchmark, it took about 7 hours from initial CAD to results. And so doing this in a legacy software, you'd be looking at, and you could see the distribution of the times of what it was required. Could be looking at 14 hours, about twice as long, and then general purpose solver could be expecting significantly more than that. So just a quick conclusion, welding simulation is able to be leveraged by welding and manufacturing engineers. This is not something that was always the case. Modeling time and effort and experience is no longer prohibitive. And in fact, the experience of the welding engineers, in my opinion, will make welding simulation better. Being able to have a GUI, user interface that simplifies many of these complexities and gives it a process-oriented approach is what's going to enable this technology. And Finite welding has made this possible.